All right. Welcome back, everybody, to day 2 of our inaugural RISE Camp. As I mentioned yesterday, we are going to switch gears from reinforcement learning that we covered yesterday to a theme on data analytics and security. And the day is going to be kickstarted by Jonas with his presentation on PyWren, real-time elastic execution. Eric.
Test. Great. All right. Awesome. So today I'm going to be talking about PyWren. Many of you might be familiar with this project from our blog posts or seeing things on the net. I'm a postdoc here at RISE. I work with both Jan Stojka and Ben Recht. And of course, all of this work is only possible because of kind of tremendous heroic efforts by Shifa and Shivram, by Shal and Alan. So people have actually asked me, what is a postdoc? And it's the thing you do kind of between having grad school and getting a real job. And a lot of what I work on is kind of this field of computational imaging. And I'll talk a little bit about that as the motivation for why we built this. So our goal is kind of explaining the project. Why did we build it? Some of the capabilities and internals. We'll talk a little bit about applications and where we're going. And then we have some exercises. And the exercises, we have about 60 minutes, depending upon how closely I finish on time for the exercises. And we'll walk you through some of those. And both the team and a few other people, I think, will be here serving as TAs. So what is PyWren? So I think of PyWren as kind of having two components, a research component and an actual tool or user component. On the research side, we're very interested in this question of kind of how do we exploit real-time elastic execution, right? Real-time and execution are two of the 4 letters in RISE, so we have to stay topical. And the interesting thing about back-end services that are these kind of function-as-a-service options like Lambda is that it means we can start asking, how do systems change when you have real-time access to 5,000 stateless cores in less than a second, right? So we're not talking hard real-time here. We're not really even talking soft real-time. What we're really talking about here is kind of a notion of, what we're really talking about is a notion of kind of deployment real-time. We're trying to get that deployment time as close to 0. On the tool side, we're very interested in this capability of building what we've been calling a cloud button. I'll talk about the origin there. Kind of how can we bring the benefits of elastic compute resources to as large of an audience as possible? In particular, a lot of underserved audiences in scientific computing. The origin of this project, so I spend a lot of time working on what's called computational imaging, right? Computational imaging is about trying to exploit physics and computation to see further and to see better. So this is fields like adaptive optics, where you can, in real time, correct for distortions in astronomy such that you can see stars or see planets from far away. Super resolution microscopy, where you can see structures inside cells smaller than the wavelength of light. Any sort of tomography or MRI counts as computational optics because, again, you're using radio waves to do this computational imaging of internal structures. Or even phase contrast microscopy, where kind of unbeknownst to most people, cells are actually transparent. But we can use computation to extract out that information and see what we couldn't see before. And so we have this weekly computational imaging lunch that we do, right? And, you know, Shivram, one of our collaborators, everyone who's been involved with AMP and then RISE knows Shivram, was up there explaining to a bunch of applied physicists and electrical engineers how to use the cloud. And one of our faculty, Ren Ng, said, well, why is there no cloud button? And of course, our first reaction, I mean, Ren has had a very successful startup. He's a very product-focused person where he's like, yeah, that's not a real thing, right? Come on. You know better than that. But he was hitting on something very true, right? Which is, as James McMillan, the founder of the Rent is Too Damn High party would say, the cloud is too damn hard. And we found that in our group, fewer than half the graduate students in our group had ever written a Spark or a Hadoop job, right? And so our group with Ben Recht and Laura Waller, primarily kind of machine learning and electrical engineering people, but it did seem like a lot of this infrastructure was just too hard for this community. You know, this is the easy list of options that you get presented with when you want to start spin up an EC2 instance. When you start doing these sort of things, you have to make kind of all these DevOps decisions about what type of machine, what instance, what base image. It goes on and on and on, and it's a lot of decisions just to get your code up and running. And so maybe the idea of a cloud button actually isn't as crazy as it sounds. And then you're going to do all this DevOps. Not fun. So our goals were as follows, right? One is we wanted very little overhead for setup. right? We didn't want you to have to think about spinning up or shutting down a cluster at all. And have kind of no persistent overhead or minimal persistent overhead. We'd like, from a developer perspective, existing code to be very, very easy to port. And for anyone who's capable of using Python, even if they don't have any understanding of distributed systems, to be able to take advantage of this. We're targeting jobs in kind of the let's say, minutes or more regime, right? We actually have those numbers down to kind of on the seconds to tens of seconds. But this is very much on kind of the opposite end of Ray, right? So whereas Ray is targeting, trying very hard to make kind of super low latency microtasks run at large scale, we're trying to get kind of elasticity on these larger or longer timescale tasks, right? I don't want to run a service, so we really want to be able to build this on top of existing cloud infrastructure provided by primary cloud providers, in particular the cloud providers that are likely to give us academic grants. And so we came up with this idea for PyWren, right? So wrens are these tiny birds that have kind of complicated songs and tend to flock a lot. And they're kind of in contrast to condors, which are very large birds. You may have heard of the Condor project from Madison, which attempts to kind of on existing legacy clusters schedule jobs. So we're thinking kind of much smaller than that. And the API for PyWren is basically map, right? And I'll talk a little bit about some additions that we have there. But fundamentally, the most important primitive here is the idea that you're going to map a function across some data. So for anyone in the data analytics space, this should not be news, right? This is something that everyone's familiar with from the rise of MapReduce frameworks like Hadoop, and then through contemporary technologies like Spark. So with PyWren, you just create one of these default executors in your code. And then let's say you have some sort of something that's iterable or some list, and you can just map that function over the list, and you get back a bunch of futures that you can then wait on. Right? And the goal here is to never really have to modify this piece of code here. You have some large legacy simulation that you're trying to run, and you would like to be able to kind of map that across, say, a set of input configurations as quickly and easily as possible. We stuck with fairly close to the Python futures interface because it's something that a lot of people with familiarity in Python know. And this depends on kind of two key underlying technologies. One is Anaconda, the Continuum Analytics new Anaconda Python distribution. And the other is a service from AWS called AWS Lambda. Now, Lambda is really interesting, right? Lambda is a microservice framework developed by Amazon that gives you 300 seconds per task. So you give it a function, it will run it for up to 300 seconds on a single core. You get 512 megabytes in temp, you get 1.5 gigs of RAM, and they have runtimes for Python, Java, and Node. And the idea behind this infrastructure is that you set it up, if you're building your application in a way that, say, when a user uploads an image, it triggers one of these tasks. You can get really kind of elastic or scalable execution, right? The demo over here with this nice little animation is that people are uploading images into S3. The Lambdas are doing something with them and sticking them in RDBMS. And then when it goes faster, he seems to smile more. I think that might be because Jeff Bezos is getting more money in this case. But that's OK. And it's not just Jeff. Google and Microsoft also have cloud functions. We'll talk a little bit towards the end about some of the kind of technology comparisons there. But everyone is kind of starting to offer this sort of a functionality. It ends up being shockingly scalable. Remember, they're handling all of this behind the scenes for you, right? And what that means is that you can say things like, hey, I want to map over 3,000 things or 5,000 things. And Amazon will just start spinning up those machines for you behind the scenes, like totally transparently. And this means that basically you get kind of perfectly linear scaling with respect to things like embarrassingly parallel computational tasks. But it's kind of amazing to get 45 teraflops out of pure Python code, right? Similarly, the other thing that surprised us was the read and write speeds to S3. So S3 is Amazon's bulk object store, right, for kind of large binary blobs. And it turns out if you have a large number of readers and writers, even though each one's only getting, say, 20 to 30 megabytes per second, right, in aggregate, that's an insane amount of throughput to a data store. And we'll talk about how that kind of might change system design. You can do a shocking amount of work with map. And in fact, part of our vision is that any place you have a loop in your code or any place you'd ever want to call map, you should be able to basically do all of that work in parallel directly inside your preferred programming environment, in this case Python, right? Most ETL tasks have a substantial map component, as well as many hyperparameter or parameter tuning type problems in machine learning. Right? And two of our exercises today will focus on kind of each of these. The interesting thing on machine learning is, of course, everyone likes to talk about how machine learning works and the singularity is near and these sorts of things. But if you ask most machine learning researchers what they spend the majority of their time doing, it's tweaking little numbers that they don't really understand what they do. and are desperately trying to kind of figure out which of these so-called hyperparameters actually gives them the best results. So we can parallelize a lot of that, which is great. So as an example, let's go through and pre-process all of ImageNet, right? The ImageNet large-scale visual recognition challenge. We can take in that 1.4 million images. We can just compute some simple features on them, right? So this is a GIST feature descriptor from some random code we downloaded off the internet. It was a great thing to try and deploy into your cluster. But we were able to run it unmodified, which is part of the appeal. And let's look at what that execution history looks like, right? So along the x-axis here is wall clock time in seconds. It goes from 0 to 250 seconds or so. And along the y-axis here is the job. So we map this over 3,000 chunks of that 1.4 million images. And there are kind of 5 phases we'll walk through here, right? One is host submit, which is when we actually submit the job to Amazon, right? Then when the green dots here are when Amazon starts the job. Red is when the setup phase is done, and I'll talk about that in a bit. And everything between basically red and purple here is actual execution on the workers, right? And then between purple and yellow here is when those are returned. You can see that we have some stragglers. You can see that there's kind of a lot going on here, and we can unpack some of that later. But if we look at these histograms, right? The start latency, basically, the time from when your machine hands something off to Amazon to when Amazon starts working with it, is down in kind of the seconds regime here. And that's what I mean by kind of real-time elastic, right? It's really amazing to me that on some faraway resource that presumably lives in the cloud, although I think that's these days a spot in Virginia, I can just instantly get access to this tremendous resource, use it for a couple hundred seconds, and then wash my hands of it. The setup time ends up taking about 20 seconds. Again, we'll talk about what that involves. But then the majority of the time is actually being spent here in compute, which is exciting. How does it work behind the scenes? Well, if we partition the world into your laptop on the left and the cloud on the right, generally how I think about the world, over here on the left, you're going to invoke map over some set of data. So you're going to map this function over your data. And what we do is we serialize that function in data. So on one hand, Python's dynamism is often viewed as an impediment to using it for kind of high throughput or scalable scientific computing workflows. But the reality is that that dynamism also lets us do all sorts of introspection to really figure out what the function is and what the data is that we need to ship over there. So we take those, we put them into S3, and then we invoke one of these Lambda functions, or we invoke many of these Lambda functions, in fact. And what happens on the other side is that the function running on Amazon's hardware inside some container pulls the job from S3. It downloads this runtime that we've prepackaged. Uses Python to run that code. Meanwhile, over here, we've tried to get the result, and so that will just block, waiting for those results to be available. And what we're really doing behind the scenes there is nothing terribly complicated. We're just polling the expected output location in S3. We save the results, we pickle or serialize it, and then we stick it back in S3, and you get the result in return, right? This is not, I say this is not rocket science, but my friends who are actual rocket scientists keep telling me that rocket science isn't rocket science. But this is not very complicated. In fact, the first prototype of this we wrote in a weekend, right? And the real insight here was 2 things. One is that the runtime here ends up actually being important, right? If you want to figure out how to kind of get your entire Python development ecosystem over to some remote machine, that takes a little bit of work. To do that, we had to make a very small snake, right? So we start with the scientific Python stack, right, in Anaconda, all the packages that we know and love. And the problem is that those all installed are about 1,200 megabytes. So to get those down to roughly 450 megabytes or so, we had to go through a lot of kind of unholy work to compact that runtime down. Because remember, we only have 512 megs of temporary space on these workers. Behind the hood, right, Amazon is spinning up a large number of these instances. Now, how do we know that? Because again, we have very little visibility into what's actually going on, right? Amazon just takes the function, it runs it, it tells us it's done. Well, we try to do host identification on these machines, right? So we look at their MAC address, right, which seems to be reasonably stable inside these containers, right? And we did some validation here. So each of these rows here is a different MAC address over that ImageNet job. And we said, hey, how stable is the timing to different servers, right? So we do this ping test, and evidently it's fairly stable. We're pretty confident these are actual machines that we're talking to. And then we said, all right, one thing we do with that runtime, remember at the beginning of a job we're downloading this, let's say 500 megabyte runtime, which doesn't take 0 time, although it's on S3 inside their cluster. So it takes about 20 seconds. But we can cache that if the next function that comes in just needs that exact runtime. And so we started plotting kind of the results of kind of how often are these runtimes getting cached, right? So the black dots here are when the runtime is cached, And the white circles here are when it's not being cached, right? Or new hosts that Amazon has brought up just to run our task. And what we do here is every 50 seconds or so, we execute another chunk of work. And we say, hey, look, how much server reuse is there? How much host reuse is there? And we see the first time there's some reuse hanging on from previous work we had done, but they spin up a couple of new machines. And we see over and over again the number of new machines that they're spinning up decreases, right? We gradually get this hot set of workers, but for various reasons we don't really understand. Some of them, we run one job on them and then we only see them a little bit later, right? And you can plot this as follows. If you try and do that kind of experiment but exponentially distance the time or space the time between job invocations, you can plot kind of time between job invocation versus the fraction of new hosts. And so we see that basically Amazon appears to be killing off all the hosts after about 30 minutes or so. And so if you try and run jobs an hour later, they're going to give you an entirely new set of hardware. But the interesting thing here is that Amazon is only charging you kind of in 100 millisecond increments while your function is running. So they're actually managing a tremendous amount of capacity behind the scenes, keeping that kind of hot for you and not charging you for it. So how are we actually using this? Right? So as I said, we do a lot of computational imaging work, right? So we do things like we take a CCD here, right, or a camera sensor, and instead of having regular optics, we just throw a diffuser in front of it, right? Because we're trying to build lensless cameras, both for consumer photography applications and for neuroscience. And you do a bunch of processing, and at the end of the day, you can actually see an image through this system, right? Without any lenses, just using a kind of a blurry piece of shower glass. And this requires us to compute a very large number of forward models, right? We have a good physical model for the system in different configurations, and we need to compute, say, 10,000 or 50,000 or 100,000 different versions of that to match to the data. And then we need to use really large-scale solvers to kind of invert the problem. And we've been using PyWren successfully there. Additionally, we do a lot of more traditional machine learning tests. So this is our sun. And I've been working with people at NASA's Solar Dynamics Observatory on data from the Solar Dynamics satellite, which generates about 1.5 terabytes of data from looking at the sun every day. And what you see here is a solar active region, right? So those are the regions that are believed to be responsible for solar flares. And we just submitted this paper where we use PyWren to kind of analyze all of this data to build a predictive model for when solar flares were going to occur. Of course, the neat part here, and you can zoom in on one of these active regions, is that actually the largest solar flare in 8 years just occurred 2 days ago. Sadly, we had not actually seen that data yet, so we did not predict that one. But the hope is alive. We also do some work in neuroscience, trying to understand a lot of this high-throughput neural data, and even kind of fake neuroscience, where we try and reverse engineer classical computing machines and see if we can figure out how they work. But the interesting part here, again, is to do this project, we needed to simulate like 10,000 or 100,000 long-term plays of various Atari games, where, unlike what you've seen lately, we were simulating every single transistor and every single wire change. So that was generating about 350 megabytes of data per second. And that all works wonderfully in a framework like PyWren. What are our current research directions? Because remember, I said there was kind of the tool component and then the systemz research component. This project that we're jokingly calling Beyond P-Space, which I'll talk about. There's this project that Vaishal, who's here today, has been working on, we're calling Lambda Pack. We're trying to get Shuffle performance to be competitive with Spark, and Shifon's done some amazing work there. And then I'll talk a little bit about kind of cloud provider comparison. And we're, of course, not the only people excited about taking advantage of these sorts of scalable compute frameworks, right? Keith Winstein at Stanford had a great, I believe, OSDI paper this year, or NSDI paper this year on using lambdas to do really fast video encoding. Josh Bloom, who's a professor of astronomy here, his startup, which was acquired by GE, had a nice blog post about doing their training random forest models on Lambda. And people like Joe Hellerstein and Johan are working very hard on figuring out what it would mean to kind of build kind of serverless database infrastructure, right? So this is not just, this is an increasingly active area of research. Now, one thing I think it's important to remember is how expensive S3 is, right? The bulk object store. But when we think about how expensive S3 is, we generally think of it in terms of kind of gigabytes per month. But if you take your dimension in, so there it's about like 2.5 cents per gigabyte per month. But remember from physics, we want to do dimensionality reduction, right? That's not a cost per gigabyte. That's a cost per gigabyte per time unit. So you can actually go through and ask this question. Some of you may remember the McDonald's dollar menu. You could say, kind of, how much can I store on S3 for $1? And how long can I store that, again, for $1? And you get a plot that looks like this. So X is your data lifetime. This is in log units, ranging from 1 minute to 1 month. And the y-axis here is terabytes, again, in log units. Right? So Amazon, for $1, will let you store 1.9 petabytes for a minute. And Amazon will let you store 31 terabytes for an hour and 1.3 terabytes for a day. Again, all for $1, which is a lot better than a quarter pounder with cheese. You can then, on top of this plot, what the PyWren read and write speeds are. That is, in 1 minute, how much data can we actually write from using some large number of PyWren workers, right? Blue is read, green is write. And we see that basically fairly quickly, right, after about 10 minutes of work or so, or 10 minutes of the 10-minute mark here, let's say that's probably more like 20 or 25 minutes, we get to the point where PyWren can actually write out data fast enough that you could do the entire job and only end up being charged $1 for it. And that's really interesting, because there's this question now you can start asking of, how do algorithms change when you have kind of what effectively looks like infinite memory, although admittedly you're accessing it through a straw. You can imagine trying to design machine learning algorithms or scalable matrix computing algorithms that never discard intermediate information if it might actually be useful. And Vaishal has a workbook a bit on that today, right? With this thing that I say we as if it's largely his baby, calling LambdaPack, right? LawPack is the famous matrix computation library. Remember, we have 3,000 SIMD cores. That's a lot of SIMD cores. Of course, parallel matrix multiplication is easy when the output matrix is small, right? And it fits very cleanly in kind of what we think of as a MapReduce framework. But when the output matrix is very large, if you're doing kind of the outer product of these sorts of things, it becomes very expensive to store this result in memory, right? For example, if n in this case is 1,000,000 and d is 10,000, then an n by n matrix that doubles is 800 megs, and an n by n matrix is 8 terabytes, right? And storing to 8 terabytes on a traditional cluster ends up being a little bit expensive, right? So our advisor, Ben Recht, really wants to figure out ways of making kernel methods work for kind of these large-scale deep learning type tasks. He's really trying to keep this alive. And so the hope is that maybe services like LambdaPack, or maybe packages like LambdaPack built on top of PyWren will let us start using kernel methods in places where deep networks have traditionally been very successful. And we do that by basically using S3 to chunk up these matrices and store the results while we run them on, again, millions of lambdas or tens of thousands of lambdas, right? And the resulting kind of runtime ends up being kind of shockingly good, right? 2,500 seconds here to generate one of these 11 terabyte result matrices with an eye towards time. This is work by Alan. Alan, my apologies. I'm going to go through this quickly. Google and Google and Microsoft both have cloud function type services, and they have varying kind of pitfalls. We actually have a blog post. Yes, sir.
The project we created named OpenWhisk.
Yes.
And I just wanted to mention something related to the fact that you say deploying the environment, all the hassle related to that. The project itself allows you to deploy a Docker image and run it as a function, and the project itself is open source. So you can't. Of course, you have to handle all the hosting, overhead, etc. that Lambda remove, but we have like a hosted solution too. So I just wanted to mention for like related to the fact I know like if you set up the whole Anaconda environment, it may take a bit of time on your timeout per functions. Mm-hmm. Well, yeah, that's it.
Fantastic, thank you. Right, so we should add IBM to this list. But the interesting thing is, kind of almost making my point, everyone's moving in this direction. I think these sorts of services are going to be very ubiquitous. And we fully expect kind of all of these limits in terms of runtime, in terms of kind of available memory and disk to expand over time. And we've already seen some of that from Amazon. And if you're in a position where you can't use the cloud, you can both use something like OpenWhisk, which we'll only be thankfully reminded of, and even packages like Kubernetes are trying to make it easy for you to deploy these sorts of systems internally. Finally, what if you have what look like more kind of traditional machine learning or data analytics workloads? So Shifan has been working very hard to figure out kind of how effectively can we use a framework like this to shuffle, right? There are these really nice large-scale data analytics challenges and where that use shuffling per dollar as a benchmark, right? And we found that if we use Redis as a backend, right? So S3 is designed for large bulk objects, whereas Redis tends to be much better at kind of smaller chunks of data. And so again, Amazon does a nice job of providing just a hosted Redis service for us. And we can start kind of spinning up large numbers of workers and large numbers of Redis shards. And what ends up happening there, I'll skip to the good part, is for these various Q1, Q16, Q94, and 95 are different queries for the TPC DS benchmark. And Shifan's been working very hard at kind of getting the PyWren plus Redis runtime to actually be very comparable to what we see in Spark, which is exciting because remember, Spark is running on kind of this dedicated large cluster that you have, right? You can spin it up on the cloud, but you kind of do all this pre-partitioning, whereas PyWren's doing this entirely elastically. So our performance numbers are looking good there, and what that starts to suggest is that maybe, especially with backends that are data storage backends that are richer than S3, we might be able to start building much larger distributed or more complicated distributed systems on top of these sorts of frameworks. So let's talk about today's exercises, right? We're going to start on it in a few minutes. Now, because the way this is working is that each of you is going to have an IPython notebook, and backing that IPython notebook is going to be an Amazon account that we're hosting. And we would like for you to both not use all of our Amazon grant money, and also to not step on each other's toes too much. So we've set kind of a 100 simultaneous Lambda limit, right? So for any of the tasks you do, that should be more than enough. But keep in mind, when you go home and try and do this, it'll be roughly, it can be up to 500 times faster if you get your Lambda limit raised to 5,000. So it's less of a Wren today and more of a plus chicken. That's okay. All the Jupyter notebooks yesterday with real accounts backing them, great. Please don't invoke more than 100 Lambdas simultaneously. We put in some seatbelts to do that. There are ways of getting around it. Please don't do that. If you're like me, you're then going to try and do that and then break everything. Please don't. Today's exercises. We have a nice intro tutorial, right, where Shifan put a lot of effort in kind of explaining everything that happens along the way and getting you kind of booted up on running PyWren. In particular there, make sure you read the text and don't simply hit Shift-Enter on everything, or when you hit Shift-Enter, you'll get some errors. And you'll be like, oh no, it broke. No, read the text. There's some things you have to fill in. It is an exercise. But for each of these, there's a solutions folder where you can just go and look at the solution if you're getting through undergrad the way I did. There's an Analyze Wikipedia one that has this nice kind of example ETL task, right? And of course, analyzing Wikipedia is a common starting point. And here in this one, we're actually directly pulling data from S3, right? There's one on hyperparameter optimization that I've been informed, if you are not familiar with scikit-learn, maybe a little challenging. My apologies there. But here the goal is to figure out which set of those hyperparameters makes your machine learning algorithm work best. And then finally, we have one on using PyWren for these kind of large-scale matrix computations. And of course, these are kind of smaller examples relative to what you do in the wild. This is from Vishal. If you're really adventurous, I recommend checking this one out. In any case, upcoming, we're trying to building more support for GPUs because we'd also like to be able to use these sorts of frameworks to train our deep nets. We're exploring ideas about an iterator interface so that you can run jobs longer than the kind of 300-second limit on Lambda. And of course, better logging and caching is a repeated request for debugging your functions. And that's it. Jay would like me to point out that everyone should re-log into their notebook by going to risecamp.tech/login and just re-log in there. That will start up a new session with kind of all of the updates and changes that we may have been pushing at 7 a.m. this morning. I don't know anything about that. And then Shivaram, Shifan, Vishal, and Alan, and myself are all here to kind of help people with exercises. So that was shockingly close to time. Any questions? Are there new pieces of paper with a password? I think they still work from yesterday. Oh, you don't have yours still. Okay, great. We'll get one? Awesome. Thank you. Yes, sir.
I have questions about the partitioning of the data. So it looks like that you kind of like partition the data into different S3 files? Is that how it
Yes.
works? So how do you control the size of that? And because that will probably affect how much parallelisms that you can going on, right?
Yes. So right now, a lot of that is fantastic. Alexi has some password cards. All of that is manual right now, right? We are not handling that partitioning. That's all kind of taken care of at the application layer. So, for example, Chiffon has spent a lot of time thinking about kind of what the right optimal partitioning is there on S3, right? If it's too large, then accessing it becomes a challenge. If it's too small, then you have all this per transaction overhead, right? And we don't have a kind of an optimal or algorithmic solution there at all, right? In general, most of the tasks that people run, they end up kind of running one per S3 key.
Okay. So the other question I have is, this looks like right now the communication is being used by the S3, right? So you put the data set. So is it because of you try to optimize for throughput but not for latency? Because that, read write to like a S3 is still have I would say that relatively significant latencies. Right?
Yes. So we are very much optimizing for throughput and not latency.
Okay.
And so of course then we started off using S3 because it was there. Right, and the kind of atomic guarantees of S3 make it not bad as kind of a synchronization mechanism, right? Because you always have these atomic rights. Chiffon's work has been exploring kind of using Redis as a backend to kind of increase that performance. The nice thing about S3 from our perspective is it's entirely hosted, right? You're not paying some kind of per hour costs or whatever. Whereas with their Redis offering, you are. You have to kind of basically spin up and manage what's effectively a machine. So our hope is that kind of by getting this to work better, we'll be able to convince some cloud providers, who knows whom, that offering kind of an intermediate point between a kind of Redis and S3 can result in these sorts of systems performing better.
Okay, great.
Does that answer your question?
Yeah.
Awesome. Any other questions? Complaints, concerns, tomatoes? Awesome, fantastic. Well,